Hey guys, welcome to the hard one. This section is limits in 3D. Oh, and I should add a goal. Let's see, how the heck do I do that? Okay, our goal for the day is to understand limits well. This is going to be a thing. I think you guys probably have an idea of how to calculate limits from Calc 1. I'm hoping for some familiarity. Because this gets a little wild, I'm going to go over it again. This might be just a little bit more formal than what you remember in Calc 1. So bear with me if there's some weird ass symbols in here. I'm going to use a bunch of animations here in a second. But for right now, I'm going to draw a couple pictures. I'm going to write down a couple of things. Give me a second to get some math written up here, and then I'll go through it. All right, so I did a little very frustrating off-camera mining here. And I've got this sentence now with some LaTeX in it. The limit of a function, f, mapping R to R, at a value A is L if for any epsilon bigger than 0, there exists a delta bigger than 0, probably depends on both A and epsilon, such that if the absolute value of x minus A is less than delta, then the absolute value of f of x minus L is less than epsilon. This is like pretty incomprehensible, I think, right? So let me rephrase this a little bit, and I'm actually just going to type this. So this is going to be a rephrase. So not formal, but roughly, the limit of a function f at a value A, so that's an x value, right, is L if for any little error in the range, right? So a little bit of error in the range, like a little tolerance in the thing we're manufacturing, right? So I'm thinking here widgets, right? I have to be able to fit the widget into a space, right? Or it has to be able to mesh with another gear or something, right? So I have to keep my manufacturing error low. Well, how do I keep the manufacturing error low? Well, I probably have to keep the error in the machine low, right? So this is that, like, okay, if I need accuracy of my product to be small, I probably need the accuracy of the machine to be much better than that, right? So this is saying the limit the limit at an x value is a limit value if for any little error in the range, we can supply an error in the domain that will result in less than the target error in the range. In other words, we're going to find some calibration for our machine that's going to get us to within that target value, right? So the epsilon is our value. That's going to be our error in the range. Delta is going to be our error in the domain that we get to control. So the kind of usual picture for this is I draw something and I say, okay, so like, let's remember back to Calc 1. We've got a value A here. I've got some freaking function. Oops, that's a kind of a crap choice for this. So I've got some function like this, right? And I'm saying, okay, I think that if I follow this up and then follow it over, I think that value there is going to be my limit L, right? So if I supply you with a range over here that we have to get inside of, you can take that and you can kind of say, okay, if I backtrack that a little bit and then follow it down here, right, I might be able to come up with some kind of error bars in the domain where when I push them through the function, I get to within the kind of specified epsilon error of L. So here in my picture, this little window is delta wide, right? So that's the radius of that little window in the domain. And this window in the range is epsilon wide, right? So this top value here is L plus epsilon, the bottom one's L minus epsilon. In the domain, I'd have a left value of A minus delta and a right value of A plus delta, right? That thing doesn't really need to be like, usually when you pull an epsilon window back, you don't get a symmetrical window. So you might notice that on this one, like this right-hand error is not quite at the dotted line. That's really hard to see on this. So let me bring up an animation. So here's my kind of one-dimensional version of this animation. So there's a whole bunch of stuff going on here. I've got a red function, and I've got a green point over here and a purple point up here. So the green point over here represents me thinking about that value A, right? So I'm going to fix that at, say, let's fix it at 1 just for ease. The function here that I'm looking at is x squared plus 2, but it doesn't really matter. Then I've got this guy, and I think the limit is probably 3, right? So someplace here I'm controlling a purple L. So I'm going to set my L to 3. So that value there is what I think the limit ought to be. This green, so this green width is controlled by this P. I couldn't make it E because E's a number, so I used the second letter of epsilon. So that value P is the kind of error in the range. So let's say I've set P to 0.434. Now, my task here is to find a delta value that'll work to get me within that that window in the range. So here, I'm going to try the same thing, right? I'm going to say, okay, well, maybe 0.434 works. So here I've got my window on the domain. That window is 0.434 to either side of 1. And then I've got this range window. That's what I'm trying to get into. So I made a couple little animations here. So first things first, we're going to lift our window in the domain up to the graph of our function. So that's this h, that's height. And so we're taking that, we're lifting it up, and then we stop. We now have this chunk, right? So that's a curve, right? That's parameterized. In fact, it's one of these. It is this one. There's another one there. So it's in fact both of those right now, but it's this one. We can see that I've parameterized x by going from a minus d to a minus d plus 2 times d, right? So I went from a minus d to a plus d using t. And then I just put that into in the y value to stick it at the right heights, right? So here I've got my parameterized curve. That's the image of my little purple thing, right? So when I pass the purple thing through the function, on the graph, I get this red thing. Now I'd like to smush that in to this y-axis to see how I'm doing, right? So I'm gonna smush with this thing. Oops, sorry, I need to turn my animation back on. So we're gonna smush that thing into the y-axis. Boom. And we see that we ended up outside of the green window. So what happened there is the delta value that I picked, 0.434, didn't work for the epsilon value that I was provided. I just didn't make it small enough. Or it was never going to work. That's also an option, right? Limits don't have to exist. In this case, it just wasn't small enough. So I can see that if I narrow this thing down, right? So if I make it quite a bit smaller, and then I'm reversing my animations here. So we're going to lift up to the graph, and then we're going to smush over, and bam, we're inside the window. This delta value worked for that epsilon value. Now keep in mind, a choice of these is not enough. This thing isn't about for a rando choice of epsilon, then there exists 1 delta. This is for any choice of epsilon, you can find a delta. It's actually pretty hard to prove that limits exist. It's also really hard to prove that they don't. So we have some cheater tricks. One of those cheater tricks is you guys know that if you have a continuous function, then the limit is the function value. And I'm kind of cheating and using that here on my little Desmos graph, right? I know that x squared plus 2 is continuous. And so no matter where I pick here, I know I'm going to be able to do this, right? You might note that some places are different than others, right? So here, let's see, what's the kind of, let me set this to something convenient. So I'm going to set this to 0.25 quick, right? So a quarter. And then I'm going to find a delta that'll work. So it looks like at the value, right? My A value is 1 right now. So at the value of 1, for a delta of a quarter, it looks, or sorry, for an epsilon of a quarter, it looks like maybe a delta of 0.12 maybe does it. We might have to go a little finer, right? But if I change my A value, oops. So if I bring my A value up a little bit, then if I bring this value up, and I'm now saying, okay, well, I think the limit's probably different if I bring A over to 2.1, right? Then the limit ought to be 2.1 squared plus 2, which is like some incomprehensible number. But let's just assume I've hit it right here. Right now I've got that L set to 6.44, which might or might not be right. It doesn't really matter. But notice that I didn't change the size of that delta window, and now it's not working. It's too big now because the function's steeper over there. So steeper functions are going to take smaller deltas relative to their epsilons. And man, you can spend some time and like find a function. So that's usually what like mathematicians do when they have to prove that a limit exists. They take an epsilon and a value A, and then in terms of those two things, they find a function that's going to provide them with a small enough delta, and then they prove that that function works. That's a little bit past where we're at in the class, and actually past kind of this class generally. But I just want you to know that's kind of how they do it. So I'm hoping this animation makes sense. If it doesn't, rewind, watch this, go click on the link, play with this animation a little bit, see if you can make this make sense. I'm going to bring up the next thing, which is going to be an animation for 3D, which is a little bit tougher, but the exact same idea. If you don't understand this two-dimensional animation yet, maybe go back, rewatch. I'll throw another couple videos explaining limits in the description because they are a little tough. So if you haven't got this yet, don't sweat it. Go use some resources, come back to this point in the video in a minute. For those of you who are following along, here's a math 3D sketch with the same stuff, right? So same thoughts, it's just in 3D. So I've got this orange surface, right? And I've got a value now, A comma B, right? And really the things that I'm gonna be changing, right? So I'm just gonna copy and paste this thing. Okay, so this is my, oops, I just dropped my pen here. That wasn't great. Okay, so this is my copy that's going to be the Calc 3 version. So let me throw some annotation on here, and then we'll go look at that animation quick. So in pink here changes. So the limit of a function doesn't. That's all same. F mapping R2 to R at a value, we're not going to be able to use A, we're going to have to use A comma B, right? Because the inputs of this function, this is taking a point and turning it into a Z value, are going to be two-dimensional. This would be the same process if this was an N, we'd just have a bunch of coordinates here instead of 2. Is L, if for any epsilon bigger than 0, there exists a delta bigger than 0, that's all the same. We're going to swap our dependency to on both maybe the point and epsilon, same otherwise, right? It just depends on where you are, such that if, and this is going to be a problem, right? So we're here going to have to swap this to the absolute value of x comma y minus a comma b is less than delta. And then that we might, what do I mean by that? Well, I really mean the distance between those points. So a dirty trick you can do here is say, if I think about all this crap as vectors and then do a magnitude to it, right? So writing carefully, that's the magnitude of the vector x comma y minus the vector a comma b. So this is the length of the displacement vector. Another way to write that would be to say, or the distance from x comma y to a comma b, right? We could just use the distance formula. So either of those options has to be smaller than delta. Then f of x minus L is less than epsilon. Great, that all works. Oh, except f of x isn't quite right. So we'll have to swap f of x to f of x comma y. Otherwise, we're good to go. Same idea. A little error in the domain, or sorry, a little error in the range needs to be dealt with. So I'll backtrack it, and I have to supply you a little error in, a little error in the range needs to be dealt with. So I'm going to backtrack it to a little error in the domain that gets me to within that error in the range. This picture is same, right? It's, you can supply small enough error in the outputs if you supply error within some amount in the inputs, right? So here's my picture. I've got here this red interval that represents the error in the domain, or sorry, in the range. So that's the kind of error bars I'm trying to get within. And then up here, I've got a value that shrinks or expands a circle around a point. So I've got a point A comma B, which I didn't put in here. Let's throw a point in there. So our point's going to be at A comma B, A comma B comma 0. So there's my point in the middle, right? So then I'm going to propose a limit. Right now I have that the limit's probably f of A and B, right? My A is 1, my B is 0.5. The function that I'm working with here is this function f. It's x squared minus y squared, right? We recognize the, yeah, which shape is that? Yeah, good. It's a saddle. It's also a hyperbolic paraboloid. Okay. And what I'm going to do is I'm just going to animate. So my animation that I'm going to run here is we're going to lift that circle off the XY plane up into the sky, right? So we're lifting that thing. We're going to lift it until it hits our surface here. You see we're lifting. I have to just pause these. Lifting. And then we hit the surface at the end, right? So we've lifted to the surface. And now if I run this projecting onto the Z, so I'm just smashing this thing into the Z axis, right? So we're smashing, and I can already see it's too freaking high, right? The values didn't quite get there. So this was me failing. See how the blue thing's bigger than the red thing? I didn't get to within the error bars. So I would need to make this blue circle smaller, right? So here's how I was controlling that blue circle, right? So I'm just going to crank down on that blue circle till it gets within the red range. And then I'm good to go. So I've supplied here, my epsilon is 0.02. And I've supplied a delta, which I called R, of 0.07 to fit within there. So this is what it looks like when a limit works, right? I think we can all agree that this surface looks nice and smooth. It's kind of continuous-y. That same thought that we had before is going to work, right? We're going to say, okay, I'm trying to plug in a value 1 comma 0.5 into a function x squared minus y squared. I can just do that. There's no division by 0. There's no piecewise anything. This is probably fine. Let me swap this function. So I'm going to call this function g, just to get it out of my way. I'm going to call this function f. So here's another function. You can notice I'm seeing the same behavior over here. This is the function x squared over the quantity x squared plus y squared. You see I've got the same behavior over here on the left. No big deal. This looks continuous. I'm pretty confident that given any red error, I can shrink the blue circle small enough. I'm going to slide A and B around a little bit. So I'm going to slide my point A, B to 0. So, oops, and I need to revert my animations here quick. So I've slid the point A, B to 0. I'm going to turn off that point because I actually don't like it. Okay, so I've got my little circle there. I'm around 0, 0. You can see you might think it's like halfway, right? I'm not getting a red error bar here. That's because f at 0, 0 isn't defined, right? It's 0 over 0. So I'm going to kind of hand define this thing. I think that regardless of what happens, it's maybe 0.5, right? And then I've got an epsilon that's, let's see, 0.02. That looks way too big. Why is that epsilon so bloody big? Oh, stupid. Joe. I lied in the other video. That was 6 times bigger than I said it was. Okay, sorry, that's my bad. Go back and amend my lies. Okay, so I've got an epsilon now of, let's say, 0.2, right? And I think my let's screw this up. Twice t. Oh, that should go from 0 to 1. Gosh, I just keep lying. Okay, there we go. No, I'm not lying. Okay, so I've got my little epsilon window here, the red thing that I have to get within, right? And I'm like, okay, so let me run my, I think being within that little circle ought to do it. So I'm going to run my little animation, right? So we're going to run our lift. So we're lifting our circle up to the graph of our function, right? This is just me imagining what's going to happen when I plug this thing in. Normally, this would be kind of instantaneous, right? Oops, we missed it. Okay, so there's a full lift. So that's lifted onto the surface here. You can see there's already some problems there, right? Because it's not conveniently touching the orange. And then if I smush it, you can see as we smush it, this is going to be better by hand. So we're smushing, 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 smushing. And you might notice that we actually covered everything from 0 to 1 in there, even though we were trying to cover somewhat less than that. So maybe it's just my delta. Maybe my delta is not small enough. So here, if I crank down on the delta, you can see it's still screwy. Right, this thing actually seems to go from 0 to 1 regardless. A little hard to see. So if you look straight down here, you can see that on this axis, it's always 0. That's the x-axis actually, right? Oops, that's the y-axis? The y-axis, it's always 0. Why is the y-axis always 0? My function here? Hang on one sec. Sorry, it's been a long day. On the y-axis, x is 0, so this fraction's 0. Then along our x-axis, where y is 0, we're talking about x squared over x squared, so this function's always 1. So there's only this one weird spot here, and it's kind of really heavily creased there. So what we see when we make those circles smaller and smaller and smaller is that crease is still in there. You kind of can't escape it. This is what it looks like when a function's limit doesn't exist, right? So this function's continuous everywhere except at 0, 0. So if we played this game anywhere else on this function, we'd be fine. But at 0, 0, that crease is in there and kind of can't avoid it. This is kind of the graphical approach to taking limits. There's a more mechanical, like algebraic approach, which I kind of encourage you to spend a hot minute learning. So there will be a couple extra videos on that, but I want you to get the heuristic from the graph first. I think that's the best way to think about this. So these animations, the links to them are in the description. I'm going to reset them all back to where I started the video. So if you need to change something, feel free to do that. You're not going to hurt any versions of these. It always shares the version that I stored. So fiddle with them, see if you can get a hang of this. Don't feel bad if this feels a little confusing. Super don't feel bad if the algebra in this section feels really crazy. This section is the tough one. Like, no joke, toughest one in the book. It's only going to get easier from here. Thanks, guys.